Hi, think of a scenario where you have to develop a deep learning model that needs to be deployed in a mobile device or in a video surveillance camera. Now, there may be plenty scenario where you may want to deploy a deep learning model in edge of a device where the device operates in a low power and low computing environment. Not only that, if you see on the other side, most of the deep learning models are not edge device friendly. Basically, the output of a lot of deep learning models requires huge memory footprint as well as compute footprint. This is where a concept called quantization comes into play. Now, quantization can reduce the size of the model by tuning the model weights. Typically, when we talk about quantization, there are two types of quantization. One is post-model quantization. So in post-model quantization, what you do is you train your model as you are training a regular deep learning model, and then you take the output of the model and then run it to a framework that will prune the weights and give you a lightweight model. In fact, I have a separate video on post-weight quantization. You can click the link on the top and then you can watch that video. The second type of quantization is quantization aware training. Now, in this video, we are going to talk about quantization aware training. So basically, quantization aware training allows for reduced precision representation of weight, similar to your post-model quantization. But in case of the quantization our training, the model is quantized as part of the training process itself, as against what we do in the post-model quantization. The benefit we get compared to the post-model quantization is you get a model with an better accuracy than what we get in post-model, because the model itself is quantization aware route. Even if you prune the weights, it will not get impacted much. Now, what that quantization does, it allows inference to be carried out using integer only arithmetic. So, which can be implemented in most of your lightweight or most of your low compute and low power hardware, which supports integer arithmetic pretty fast. So in this, let's get started with the video. I'm going to show you how to develop a model which is quantization aware. So I'm going to must make sure that in the collab I have a GPU environment. So if you click on it, I just want to make sure that I have a GPU allocated, because the training is going to not take a lot of time, but in GPU it will be faster so that I can complete within the video itself. And I have a GPU allocated. I have a Tesla K80 GPU. Then I'm going to install an package called Tensorflow Model Optimization. This is the package that has your libraries required for quantization. I am also importing TensorFlow 2.x. I'm making sure that TensorFlow 2.x is there, and I have a TensorFlow data sets which I have imported, that is used to download the data set. I'm going to use the MNST data as fashion means data set for from there, and then I also loading the TensorBoard extension over here. I have run this already. I'm just making sure that I've already installed it. I don't want to install it during the video process. I've already installed it. I'm making sure the GPU is allocated to us. So basically, when I say the TensorFlow config list physical devices, it will show me what devices I have. I have a GPU and a CPU, and I have a XLA compiler, which is optimized compiler that TensorFlow uses to compile the network graphs. I have that. And then what I'm doing is I'm importing the TensorFlow datasets, and I'm downloading the fashion MNIST dataset from TensorFlow dataset. So it will give me a train and test split over there. And I have already downloaded this. It will take like some 2 to 3 minutes. I have already downloaded the fashion MNIST dataset. And the output I am assigning to a dataset variable and an info variable. So when I print info over here, you can see a whole lot of information on the data set. But what I'm going to do is I'm going to print specific columns. I'm going to print what are the features available, basically the number of classes and the names. That's it. So if you see over here, I have a image and label feature. So image is a 28 by 28 image, and label is basically telling me the 10 classes the fashion MNIST data set has, and these are the 10 classes. It is t-shirts, trousers, pullovers, dress, and other thing. So the very first thing I'm going to do is I'm going to split this data set into train, test, and validation. The train and validation I'm going to use as part of the training process, and test is I'm going to test to see how well our model perform. So what I'm doing is a data set is the variable I assigned on the top. I am taking the data set 0 and 1. Data set 0 is train and 1 is test. If you see over here on the top, my split is basically train and test. So 0 is train and 1 is test. right? So I am assigning it to assigning to like fm underscore train and test, and I'm creating a validation data set from the test data set. So what I'm telling the validation data set is take the first 3000 records and assign it to the validation data set, and then skip the 3000 records and I'm assigning it to the test data set. So basically what will happen is if I have 10,000 records, the 3000 will get assigned to validation data set and the remaining 7000 will get assigned to test data set. So let me run this. I'm just going to print the fm train. Fm train is basically a tf data set data type, and then let me print the length of the train data set. So in the train data set, I think it has close to around 60,000 records, the fashion mnest. So this will take some time to print it. Next, what I'm doing is, while it is printing net, next what I'm doing is I'm importing the matplotlib library, and I'm importing the numpy package to visualize the output of the train data set. So in this case, if you see over here, I'm taking the fm underscore train, and I'm taking the first 5 records in the fm underscore train. So it came out, it has 60,000 records, first 5 records, and then I am splitting it by image and label. If you saw the output of the data set, there's an image and label. So basically the fm train has image and label in that, and then I'm just plotting it, plotting the image and label and printing the label and category of that particular image. So once I run it, you can see basically all the 5 data is printed. The label for this is a coat, this is the top one is a coat, and bottom one is a trouser. So I'm just visualizing the data set. Now what I'm going to do is I'm going to start preparing the data set for my training process. So in the training process, this is going to be pretty similar to how you train a regular TensorFlow model, but I will show you the difference. Like once we start training it, we will make sure that the model is quantization aware here, right? So in the pre-processing step, what I'm doing is I'm taking the image and label. I am dividing the image by 255. I'm just normalizing the image, and then I'm returning the image and label variable in the scale function. And then I have created this one function. I have created one more function called get data set. What the get data set will do is it will take the train, test, and validation data set and call the scale function, and then it will return a trained data set scaled, the scaled version of train, test, and validation data set. So these are the 3 data set that will get returned to me. I'm given batch size as 256, so that it runs faster. I can give any lesser batch size as well. All right, so I'm just shuffling the train data set to make sure it's seeing a different version every time, right? So let me run the scale. Let me run the scale function, and let me run the get data set function. Then I'm creating a function to create the model itself. I'm using Keras over here. So what I'm doing is I'm creating an convolution neural network. It's an image. So I'm creating a convolution neural network. I'm creating a convolution 2D layer with 64 filters, 128 filter, and then I'm flattening it out to 256 filter. I'm using a typical, it's a typical simple network model. I'm just introducing dropout so that it does not overfit. And then finally, I'm having a dense layer of 256 where I'm flattening it out. And then finally, I'm having a dense layer of 10. That is the number of outputs we have in the classes. I'm using activation function softmax. Now till here, it's going to be pretty same than the similar to your typical TensorFlow model. Now what we are going to do is we are going to apply quantization over here, and we will apply quantization to the whole model and then see the model summary as well. So what will happen is, like, your model is same. The only thing is the quantization that we introduce will introduce a quantization layer in the output of the model itself. So basically here what I'm doing is I'm importing the TensorFlow model optimization framework. I'm calling the create model method. And then from there, I am calling the TensorFlow model optimization quantized model package. And in the quantized model, I am passing the model object, the Keras model we created on the top. And then what I'm doing is I'm just compiling with the compiling that particular model with the typically Adam optimizer. You have the categorical cross entropy and the accuracy as the metrics, which is very similar to a TensorFlow model. But here I'm using the quantization aware model. So what I'm doing is I'm creating a quantization model, and then I'm passing the model itself to the quantization model. Now my model becomes quantization aware, and then using that to compile the model, and then I'm printing the model summary. So if you have seen a typical TensorFlow model, you will get all the layers like convolution 2D or the max pooling and everything. But here if you see, a quant is appended to each of the model. So this is telling the, okay, now the model is quantization aware, and we are going to use this model to train the output, right? So that's what we are going to do. So yeah, I'm just like creating a log directory so that I can use TensorBoard to visualize it. Now then I'm calling a TensorBoard callback function. I'm calling the get dataset method on the top that we created, which will return me train, test, and validation dataset. I'm putting both the train and validation dataset in cache, and then I'm calling the quantization aware model.fit method. I'm passing the train dataset. I'm just training it for 5 epoch, just for the sake of this video. But if you want to train, you can train for more epoch. And I'm calling the TensorFlow callback function so that I can visualize this in the TensorFlow. I'm using validation data set to make sure my network is evaluated on every epoch to see how it performs. So let me start the training. Now at this stage, right, since it's a quantization aware training, basically the resulting model that is coming out is just quantization aware, but it's not quantized, right? So what we are going to do, the output will still be float 32 weights. We need to convert that float 32 weights into an integer 8 weights. So we will see after this, once the model is there, we will check the size of the model, and then we will also see how to quantize the model finally, right? Since it is quantization aware, it has learned during the training process itself how the quantization output will look like, not like the post model quantization. So this is going to take some time, and you can see basically in the first epoch, the accuracy is 82, the validation accuracy is 86. Till now the model is not overfitting or something like that, but let's wait for some time until this completes. So the idea is like, once you have this model, once you have the quantization aware model, or even in the case of the previous video on post model quantization, this model can be directly deployed into an edge of a device because it is doing an integer arithmetic. Lot of hardware supports lot of low compute and low power hardware supports integer arithmetic very fast. That is one aspect of it. The second aspect, I didn't cover a lot of TensorFlow stuff over here, but if you are looking to get more details on that, I have a similar model developed purely on TensorFlow. You can click the link on the top and you can watch the TensorFlow video where you will get more details on it. So again, we are in the third epoch now. You can see the accuracy is around 88%. Let's just keep monitoring it over here. Right. Now, so there are a couple more steps over here. Yeah, and so one more thing is like, you need not really use it only in the edge of a device. Sometimes you want faster inference, right? You basically, we know neural network model take a lot of time to inference, and you need a GPU when you want to speed it up. But when you are deploying in a business process where the exact accuracy does not matter and you want faster inference time, you can use this quantization hour model to deploy with your normal business process as well, not only on the edge of a device, right? So our validation accuracy is slightly down than the accuracy, but still I would not consider it's overfitting. It's overfitting as of now. So it's around like 90%. We are in the last epoch. So once this is done, I'll just move on to the uh, as the training is going on. I'm going to save this model in the local folder, and then what I'm going to do, I'm going to print the output of and see like how the size looks like. Now the final model is around 89% uh, uh, accurate, not as great as the previous one. Typically in the real world, I want to put a early stopping, or I want to pick a model that is accurate. But now for this case, I'm just going to go with the final model. You see the output of the model over here. It is around like 6 MB. Yeah, it is around 6.5 MB. Right now, we are going to take this and apply quantization. Before that, let me check the tensor board, and in case you want to visualize like how the validation of the network look, you can visualize that in the TensorFlow. You can see basically it was good till the third epoch, and then in final epoch, basically there was an site overfitting. But for this demo, I still use it. Maybe I want to increase my network complexity. I want to add some regularization. I need to check that out, what I need to do. You can also click on the graph and visual uh, some local notebook traveler, but you can see You can see, if you click on this, you can see like all the layers and everything over here, right? But to the quantization part, I'm going to run the NVIDIA to see my memory utilization. Since I'm using GPU, I'm just using around 1 GB of GPU against the 11 GB that is allocated to me. Let me use this quantization of our model now and do an evaluation on the test data set. So let me run this. What is going to take the test data set and see what is the accuracy, and it's the accuracy is close to 89%, which is very similar to our validation accuracy. So the model is pretty much fine, right? Now what I'm going to do is I'm going to take the model which is 6 GB, which is 6 MB, and I'm going to apply the quantization right here. And for that, I'm using the TF Lite converter framework. So what I'm going telling is I'm telling the TF Lite converter use the Keras model I have created, that is a quantization of our model, and I'm telling for the optimization use the default optimization. Now there are multiple methods over here you can use. You can optimize it for latency, you can optimize it for size, but I'm just going to use the default optimization that the TF Lite framework is feels it's good for the model. And then I am going to convert that model. I'm just going to use this converter object and convert the model into a TensorFlow like model. And in the next step, I'm just going to print out and show you what is the model size. So once this is converted, the 6 MB model that we have seen is the size will get reduced. Now you see it's only 1.6 MB. So almost you're seeing around 4x reduction in size. So now the model is pretty lightweight, right? And then I'm going to take this model and do the inference and see is there any loss in accuracy, right? We know when we strip off the floating to integer point, there may be some loss. There might be, there might not be also. So we are going to see if that is the case. So I'm going to click on, I'm going to like start the TensorFlow right interpreter to kind of do the inference, and then I'm just going to allocate all the tests, right? So that's what I'm doing, and from this particular interpreter, I am taking the first the input layer and also the output layer of the particular model that we have converted. So it is assigned to like input tensor index and output index. So that is what I'm doing over here. If I print the get tensor detail, it will print all the details of that particular model, what the model is, whether it's quantized or what is it. If all the information is there just for the information. But let me go to the prediction part now. So I'm creating an array which is a prediction output. I'm creating an accurate count over here, telling like how much of the model, how much of the outputs were accurately predicted. I'm just creating a count over here. I'm taking the text test data, the FM test that I created on the top, and I am mapping this is the raw data I have initially, not the scaled version. So I am calling the scale function over here. Then I'm passing to the test image. And then what I am doing is I'm just expanding the dimension of the test image over here. And then I am calling the interpreter, which has my TensorFlow Lite model. I am setting the tensor, which is the input tensor that I have given over there, and I am passing the image object. So I have the input tensor and the output tensor now. In the input tensor, I am passing the test image, and in the output tensor, I will get the output of the model, right? So I am invoking the interpreter, uh, and then I am basically calling the output index, which is my output index object I have created. I'm calling, I'm doing a argmax. Basically, it will give me the maximum predicted probability, that is the output class, and I am appending it to the prediction output. And also I am comparing if the output is equal to the test image. The test image, basically, if you see over here, the test image will have the true label as well, right? This is the out is the predicted label. I am getting the true label. I am comparing it. If it is equal, and then I am adding an +1 to the accurate count. That's what I am doing over here. And once this runs, I am just taking the accurate count and dividing it by the length of the total, right? So basically, how much is accurate out of how much image. That's what I am trying to do over here, and then I'm finally printing the accuracy. And you can see over here, after the model is converted as well, the accuracy is almost like 89%. In some cases, you may have slight drop of accuracy, and in post quantization, you may there's high probability of having it, but it will not be that okay, your model is 89% accurate and the quantized model is going to be like 80% or something like that. It will be close to 89%, and that's what we are seeing as well. That there was not major drop in accuracy. So this is about quantization aware training. And what I'm going to do is all the videos. I have a video on edge analytics and model quantization and post model quantization. I'm going to put it in the video description below. You can click and watch the related videos. This will help you deploying the model in the edge or deploying in a environment where you need faster inference time. So that's about it. Thank you very much.